In this video, I'd like to discuss the stereochemical implications of substitution reactions with a particular focus on SN2 reactions. And I would very much like to explain why we always see a backside attack in SN2. That is to say, why the nucleophile always attacks the electrophile from the side opposite the leaving group. So let's consider a really simple example. And let's imagine here's our leaving group on iodine. And let's simply draw this molecule here, H. This one will be, let's say, methyl. And here we can make this one an ethyl. Okay, let's draw CH2, CH3. Okay, so this is a chiral center now. This is a stereogenic center. We have 4 different groups around that carbon atom, and it is chiral. Okay, so nucleophile comes in and attacks the electrophilic center right here from the side opposite the leaving group and displaces the leaving group. And actually, what I'd like to do is focus for a moment on the transition state. And the transition state will actually help you visualize the inversion that's taking place. So we have our central carbon atom, and it's going through a trigonal bipyramid transition state, which is sort of pentavalent. And I'll keep the stereochemical designations here just to make it sort of clear. This bond is being broken, and this bond is being formed. So this is the transition state for an SN2 reaction, where these 3 groups are going from sort of being a tripod facing down to becoming like a tripod facing up, we can say, something like that. And so the product is going to look like this. And we get this, and we get this, and we get this. And so we've inverted this center, actually, by doing the substitution, by substituting this iodide leaving group for a nucleophile, we've inverted the center. So I'm not sure what the stereochemical designation is here. Let's say it's S. If this is S, then now this is R. The center is R. So when we do an SN2 reaction, it goes through a transition state. Let's draw the sort of tripod model, we can say. So where, like, let's say you have this. You kind of have like this tripod type structure. It goes through a transition state where the tripod sort of becomes trigonal bipyramid, as sort of each of these groups are coming upward like this. And then finally, when it's done, these 3 groups have inverted and they're going the opposite way. So it's inverting through this center. So this is the product, this is the starting material. So this is the idea. This is the inversion that you see in SN2 reactions, actually. Okay, so let's give a concrete example. So let's say we have this system right here, and we will choose, let's say, this as our nucleophile. Here we have the nucleophile, and of course here we have our electrophile, delta positive right there at C2. Well, the nucleophile comes in and attacks from the back side of the leaving group and displaces the leaving group. And what do we get? We get our product with inversion of stereochemistry. And you can say plus HI in this case. I don't think that's always entirely necessary, but in any case, this is the product that forms from these starting materials. Now, the question before us is, how do we explain the backside attack? It's clear that if there's a backside attack, certainly the stereochemistry is going to invert. We've shown that, but why is it that there's a backside attack? Okay, so let's consider this molecule again that we've just shown. And if we consider it from sort of an orbital perspective, then what you can see is that the bond is basically a couple of orbitals overlapping to form a bonding interaction. That's in fact what a bond is. It's the overlap of electron clouds of orbitals. And so the bond here is basically a pair of bonding orbitals. Now, there's also an anti-bonding orbital, and I'll draw that as well. So this is what the anti-bonding orbital looks like. And here's your iodine. I'll actually draw the bond right here. And so this is the anti-bonding orbital with respect to the carbon and the iodine. And so what happens is the nucleophile populates the anti-bonding orbital with respect to the carbon-iodine bond. And by populating the anti-bonding orbital, the bond weakens because the anti-bonding orbital is anti-bonding with respect to this particular bond. So the nucleophile populates it with electron density, it breaks this bond, and we get our product as mentioned above, which is, in this case, it's the sulfur, but I'll just put the nucleophile because that's what we drew. And the thing to remember is that the anti-bonding orbital is always 180 degrees opposite the leaving group because it's 180 degrees opposite the bonding orbital. So the bonding orbital is here in between the two atoms, and the anti-bonding orbital is opposite the two atoms. It's over here. And so therefore the anti-bonding orbital is always going to be on the other side of the bond with the leaving group. And that's the reason the nucleophile always attacks from the back. It's because the geometry of the orbitals is such that the anti-bonding orbital extrudes from the back side of the carbon leaving group bond. And this is actually the reason that the nucleophile attacks from the back. And by attacking from the back, obviously, we can see that quite clearly it's going to invert the stereocenter. And so the conclusion to draw here is simply that with SN2 reactions, a couple of things to remember. The first is that you get a backside attack, and the second is that it inverts stereochemistry. Okay, so the SN2 proceeds with inversion. Okay, always proceeds with inversion. Now, SN1 is quite a bit simpler when it comes to the stereochemical implications. And let's talk about the exact same system. This one right here. Well, with SN1, as we know, the leaving group simply leaves. And in this case, it's going to leave behind a secondary carbocation. And in this case, you can imagine this molecule right here sort of sitting in the plane of this particular plane right here, sort of sitting flat. Well, if you think of a nucleophile, the nucleophile has a 50% chance of attacking this carbocation from the top, and it has a 50% chance of attacking the carbocation from the bottom. So in other words, we get a statistical distribution of products because the carbocation is in a p orbital and therefore it's planar. So that what you actually get in this case is you get 50% of this, and you get 50% of this. And what we call this in organic chemistry is a racemic mixture or a racemate. So SN2 proceeds with inversion of stereochemistry, and SN1 simply racemizes. Any stereochemical information we have in the starting material is completely and totally lost in an SN1 reaction because it goes through a planar intermediate where all of the stereochemical information is lost. So SN1 racemizes.